afternoon session of this workshop. And it's a pleasure to introduce the first speaker, which will be Alexander Varchenko. And he will talk to us on determinant formulas for pairing matrices of arrangements of hyperplanes.
Thank you for inviting me to speak here. So I'm from a different mathematical community, so I will not manipulate with Gaussian integrals and will not consider cluster expansions. So for some of you it will be a relief, but for some disappointment. I will talk about determinant formulas related to arrangements of hyperplanes. Determinant formulas for arrangements of hyperplanes. So the source of such formulas is what is called the theory of general hypergeometric functions, general or multidimensional hypergeometric functions. The simplest example of such an object is the following integral from 0 to 1, which is called beta function. A1, A2 is t to the power A1 minus 1, 1 minus t to the power A2 minus 1 dt. And according to Euler, this is equal to gamma of A1 multiplied by gamma of A2, gamma of A1 plus A2. So this is an example of a formula that I will be discussing today. So in this case, we have an arrangement of hyperplanes on the line 2 points, 0 and 1. With an arrangement of hyperplanes, we associate a matrix of some integral, hypergeometric integrals. In this case, it will be a matrix, 1 by 1 matrix. And then I will give a formula for the determinant of that matrix. And this is that formula. In all formulas that I will give you, they all have the following flavor. The matrix, the entries of the matrix, will be global characteristics of the arrangement. So you need to integrate from 0 to 1, while the determinant will be the product of local contributions. Local means you consider some intersections of hyperplanes. In this case, these are just hyperplanes. And for each of them, to each of them, you assign some factor, and then you have the determinant is equal to the product of local factors. I know that the word factorization is one of the favorable words here. So in that sense, I will be discussing factorization of some global object into local factors. So in general, what we will do, we will consider an arrangement of hyperplanes in a real space. So we'll consider C an arrangement of hyperplanes H1, Hn lying in the real space. Hi hyperplanes. We will choose an equation for each hyperplane. So we will choose linear functions fi on the real space such that hi will be defined by the equation fi equals 0. Then we will choose exponents or weights for each hyperplane. So it will be a, a1, an. You may think that they are real numbers, or usually they will be numbers. Sometimes they will be just parameters of some future considerations. And then I will consider the function phi a, which will be the product of all these factors raised into the power, corresponding powers. So numbers. At this point, product over I from 1 to n. Then the next object, so this is the function. Now I want to choose a differential form for any set of indices I1, In, distinct indices between 1 and distinct indices between 1 and n. I will define the differential form, the logarithmic differential form, dfi1 divided by fi1 dfin divided by fin. So this is a form which has simple poles at the chosen hyperplanes. Then what I will consider all these hyperplanes, and I will choose connected components of the complement. I will take any connected component of the complement. So domains delta, which will be connected components of the complement to the arrangement. And then I will consider the main object, the following matrix. I will integrate this multi-valued function A using one of the form and using one of the domains. And this will be called the period matrix. The period matrix. And so my formulas will be for the determinant of the period matrix. And the formula will be of this type. So they will be product of local contributions, where contributions will come from the edges of this arrangement. And an edge is any non-empty intersection. An edge of an arrangement is any non-empty intersection, intersection of hyperplanes. Yes?
You mean that it is a matrix in the indices delta and I?
Delta and I, yes.
Which are show to the n.
Which are what?
The cardinality of possible deltas and of
possible i's, yes. We will be a little bit more careful when we will write true formulas, but the period matrix is you take arbitrary domain, you take arbitrary differential form, you integrate, and you will have this many different integrals. Like in this case, you see, I am contradicting to myself a little bit. In this case, we have two hyperplanes, three domains, but I took only one of them. So I will be a little bit more careful in choosing domains. At some point, I will say, let us choose only bounded domain. And at some point, I will take, let's consider all domains. Other questions? So, but anyway, this is a very naive direct construct.
Where does the name period matrix come from?
Period matrix? You know, from algebraic geometry. You know, these are differential forms. These are, in some sense, cycles. And you see, when you take a basis of cohomology, I don't know, holomorphic forms over periods, then you will have what is called period matrix. Now, in this object, what we will have the following. We will have these deltas, and we will interpret them as some homology group, some homology group. So Hn. Then we will have these differential forms. We will interpret this as some cohomology group. Hn. And then there will be this hypergeometric pairing when we will take a homology element and a cohomology element, and then we will get numbers. So this will be our period matrix. And it turns out that in this case, you may construct three bilinear forms. One is on homology groups. One is on cohomology groups. The other, this matrix is already given, period matrix. And it turns out that in all these cases, the statement is true, that the determinant of that matrix is equal to the product of local contributions. So this is not because of you consider the integral. It is not because you consider combinatorics. It is not because you consider differential geometry. There is some higher reason probably for this splitting of global object into determinant of a global object into the product of local objects. Now, let me start with the matrix on this homology group. So for some reason that I will explain later, it is called a quantum bilinear form of a real arrangement. So it is what I consider. We consider a real space, a finite set of hyperplanes in it, and we will also assign to every hyperplane a number, a weight. And so I want to define this bilinear form. I will call it A. And so this will be the following thing. So assume that I have this arrangement, and assume that I have these two domains, any two domains. Then I want to define the scalar product, P and Q. So this, what I will write now, reminds me some formulas from the first talk. So this will be the product of weights AI, where the weights should be such that HI separates P and Q. So you have two domains. So assume that this will be A1, A2, A3, A4. So here, every hyperplane separates those two. So in this example, it will be the product of all four factors. But say if I take this domain and that domain, then it will be separated only by A3. And in that case, it will be just A3. You can think about them as about numbers or as about some variables. And this will be a bilinear form. A is a bilinear form on the space, I don't know, M of linear combinations of domains. So in this case, it will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 by 11 matrix. Clearly, this is a symmetric matrix. So scalar product of P and Q is equal to scalar product of Q and P. And let us consider an example. So let us consider that arrangement. And we have A1, A2 weights of those two hyperplanes. And we have P1, P2, P3. And then we will have this 3 by 3 matrix. 3 by 3 matrix. So the scalar product of P1 with P1 is 1. Nothing separates any domain from itself. Now, P1 and P2 are separated by A1. P2 and P3 are separated by A2. P1 and P3 are separated by both hyperplanes A1, A2, and A2. So the form is symmetric. It turns out that its determinant is equal to 1 minus A1 square 1 minus A2 square. So it turns out that this is a global characteristic of the arrangement. Who separates who is encoded in this matrix. But the determinant is the product of local characteristics. So you consider all possible edges in that arrangement, and you for every edge you take, in this case, for every point you write this thing, and this will be the determinant.
Square is outside or inside the...
Repeat again?
The square is outside or inside the parentheses?
This square today is, yes, I chose both possibilities. So they are of this type at this moment. Okay, now in general, we do it as follows for an arbitrary arrangement of hyperplanes. So we will define the weight of an edge. So the weight of an edge is an edge A. L is an unempty intersection of hyperplanes, is equal to the product of all weights such that HI contains that L. So, so if you have, for example, this edge, if this is L, the intersection of two hyperplanes, then its weight is A1 multiplied by A3. In more general situation, you may have more complicated edges. And the theorem says the following, that for arbitrary real arrangement, the determinant of this form A is equal to the product of local contributions. So you take 1 minus A square of L, and then you raise it, the product is over all edges of L of that arrangement, and you raise it to some power L of L, which is called L of L, discrete volume of L. So, and this is a non-negative integer. L of L is a non-negative integer. I will skip the definition of that negative integer, but the global characteristic, the determinant of the global characteristic is the product of local contributions. So this is my main claim. And let's consider an example. Assume that you have in a plane, you have hyperplanes A1, not hyperplanes, lines A1, AN. So you have n lines intersecting in one point. In that case, the matrix will be 2m by 2m. There are 2m domains here. And in that case, the determinant of this A is equal to the product of the following. So you write from, so what are edges here? This vertex and this those lines. So for every line, you will have AI square, and then multiplied by times 1 minus A1 AN. So this is the weight of that vertex to the power n minus 2. N minus 2. To the power n minus 2. So in this example, that discrete volume is n minus 2. So somehow it counts how many points, how many hyperplanes come to that edge. As well, it counts for this hyperplane, the weight is 2. It counts how many domains are on that hyperplane. So this discrete volume is something like this. So you count how many domains are on this edge intersected by transversal hyperplanes. And you count also how many domains come to that edge. And then the product of those numbers is equal to that thing.
But what could you review what you mean by an edge?
An edge is any non-empty intersection of hyperplanes.
So an hyperplane itself, or a crossing of two hyperplane and so on. So it has a dimensionality. There are edges of various dimensionalities.
Yes, yes. Yeah. Yeah.
Like if one makes the cell decomposition, something like that.
Yes.
Okay, so this is the formula. Now, one of the most important examples of arrangements is the arrangement of diagonal hyperplanes. So in Rn, you consider the hyperplanes Hij defined by the equation xi minus xj is equal to 0. So in this case, the domains are labeled by elements of the permutation group and this domain delta sigma is equal to the set of x's defined by these inequalities. X sigma 1 is less than x sigma 2 is less than x sigma n. So now, this form is defined on M. In this case, will be the linear combinations of the element of the symmetric group. Now, assume that you have all weights are equal to the same number. Then, in this case, our form will be the following form. So you take two permutations, and you write that this is equal to q to the power length of sigma nu inverse. And this is an invariant scalar product on this group algebra. So what?
The length of a permutation?
Repeat?
The length of a permutation is the number of fixed elements.
The length of the permutation. The length of the permutation.
It's defined as
Number of inversions.
Number of. So you write it as a product of
Transpositions.
transpositions, shortest possible way.
shortest number of transposition. Okay.
So which in geometrically means this is how many hyperplanes you want to intersect when you go from one domain to another. So you can define this number as the number of hyperplanes you are stressed to intersect when you go to the first, from the first to the second by a straight line. And so this is an interesting object from the theory of representations of the symmetric group. So in particular, so what is the formula saying? That the product, the determinant of this formula is the product of 1 minus q to some power. And in particular, it means that if q is small, repulsive, I forgot how you call it, then A is positive definite. A is positive definite. Non-degenerate and positive definite. I will also hope to produce this word n factorial as I should. Okay. Now, after the previous talk, I thought that I need to make the following remark. So this length, sometimes this discrete volume, sometimes is 0. Sometimes it's 0. And in that case, that edge will not contribute. So in this case, not all edges will contribute. So in the previous talk, there was this arrangement of diagonal hyperplanes considered at some moment for some counting problem. So in that case, not all edges contribute, and most of them will give 0 contribution. So in principle, this formula will tell you that this global determinant is equal to 1 minus weights of edges to some powers, and those powers may be of combinatorial interest from the point of view of the previous talk, but I did not think about this more carefully. Another interpretation of this is the following, of this arrangement. So instead of delta sigma, you will, this delta sigma, you may interpret it in the following form. You write instead of it f sigma 1, f sigma n. So what you have? You have variables, non-commutative variables f1, fn. And a domain is the same as a monomial in non-commutative variables. And what I am defining here is some scalar product on monomials, on non-commutative monomials. And it turns out that this is a very important observation, that if it happens sometimes that you need to consider scalar products on linear combinations of non-commuting monomials, and then this is how you do it. Let me consider another relation. Yes?
How do I see that? How do I see that this is a domain this product of non-commuting.
What is a domain? Domain
It's
is
just by definition.
by definition. Domain.
Okay.
I am saying I can interpret this in different ways. For example, domain as a permutation, domain as a product of non-commutative variables. And in that sense, I have from this construction some scalar product on this algebra, non-commutative algebra. And
Well, does non-commutative mean the product when you switch the order of the sign change?
I am not going to switch. I don't have any way to switch them. You know, I am just saying that I will call this domain delta sigma, sigma, or f sigma 1, f sigma n. This is just my notation for it. But so right now I'm not switching anything. But let me continue a little bit, and I will switch.
Each subscript occurs at most once.
Yeah.
Yes, yes. No repetitions. No repetitions.
Just to be sure, these f has nothing to do with the original f being a linear function.
Yes.
New names.
Yes. Let me call it T1. I will call them F capital. No, I will have some reasons to call it F capital. Okay. Now, the next step, very important step, is the following: that maybe let me start with an example. Let's consider the same arrangement, but in R3 of diagonal hyperplanes. So there are 3 hyperplanes, and I have this arrangement in R3, that arrangement, n equals 3. And let us, here I consider, let us take all weights to be equal. But now let me consider the following weights. This will be Q, this will be Q, and this will be Q inverse square. Then this arrangement has a symmetry. I can reflect it with respect to this horizontal hyperplane. And under this symmetry, so this is part of while group. Under this symmetry, this hyperplane will go to that, that will go to that, this will stay. And the weights are preserved under this permutation. So, you know, the formula is so naive that it will preserve the scalar products under this reflection. And so in such a case, we may split the 6-dimensional space of domains, linear combination of domains, into 2 subspaces of invariant subspaces and skew invariant subspaces. So in that case, M will be equal to 3-dimensional subspace symmetric and 3-dimensional subspace skew-symmetric domains. And the scalar product of the domains of different type will be 0, because, you know, one is multiplied by 1 under the reflection, the other is multiplied by -1, so the scalar product must be 0. Let us consider this, for example, space. So it will be 3-dimensional. So what it will be the basis in M3? In basis in M3 will be this domain plus that domain, this plus that. Or it can be this domain plus that domain. Or it can be this domain plus that domain plus that domain. So this is a 3-dimensional space of invariant linear combinations. Now it turns out that this form is degenerate on this space. And you can write the kernel of that form. A restricted with these weights, restricted to M plus, has kernel. By the way, I was going, okay, so has kernel. And the kernel has the following form. So that domain plus Q inverse that domain plus, I said minus, and plus that domain is an element of the kernel. So you usually meet this this object in the following form. Usually you write it f1 square f2 minus q plus q inverse f1 f2 f1 plus f2 f1 square, and this is called the left-hand side of the Serre relation. Serre relation for UQ quantum group corresponding to SL3. In SL3, you have generators F1, F2, E1, E2, and you impose in this quantum group relations like this. This element is supposed to be 0 in the quantum group, and this is not like a numerological correspondence. It is because you can interpret indeed such a form with suitable weights as this Killing bilinear form on the corresponding part of the quantum group, and then kernel here is the kernel there, and so this is geometrization. This arrangement with special weights and this bilinear form is a geometrization of some part of quantum groups. And so this is another relation of that form to something more familiar from other subjects. Okay, maybe I will. Okay, now in general, so I want to ask the following question. So in general, assume C has assume a finite group G acts on Rn linearly, preserving the arrangement and the weights A. In that case, the space of all linear combinations of domains splits into the direct sum of isotypical components. Mi are isotypical components of G action on that space of domains. And then the matrix A will have the block form A1, A2, AN. And the product of determinants is known and is equal to that formula which I mentioned previously. But the question is, what will be the determinant of AI? What will be the determinant of AI? It turns out that in all nice examples, in simplest cases, when you can calculate, the formula is very, very nice. It's the product of, again, of some monomials, but in the right-hand side of this type. But instead of 1, it will be some root of unity, or anyway. So this is an open problem. What is the determinant of an isotypical component? Now,
is it for this particular diagonal type of, or for any arrangement?
For any arrangement, it's an open problem, and for this, as far as I know, also an open problem. Or describe the kernel of the. Assume that you have such a situation, then you have these blocks, and sometimes the blocks can be degenerate, and then the question is to describe the kernel. Like in this case, I consider it an example, and on M plus, the form was degenerate, and I describe the kernel of it.
Sorry, just what's the isotypic decomposition again?
You know, the group acts on this vector space. You can decompose it into irreducible representations. You unify all irreducible representations of the same type, and this will be called an isotypical component of an action.
It acts on the vector space of formal combinations. Of
Yes. When the group acts on the space and in preserving the arrangement and weights, in particular, it acts on the domains of the complement. And so you can ask such a question.
Can I ask if I well understood? the reason because there is a non-empty kernel is that
The reason because of what?
there is a non-empty kernel in that example is that because there is q and q minus 2, so when you take, for example, the product of all the three, you get 1 minus 1 squared, which is 0.
Yes.
So it can only happen in places where you have sufficiently weights in order to produce a 1.
Of course, the kernel can appear only if one of them is 0. So there must be an edge so that the product of all contributions to that edge will be 1.
But is it true that we shouldn't, with what you told us, we shouldn't be able to reconstruct, for example, that linear combination f1 squared at f2 and so on? For example, I haven't understood how to produce it.
How to produce that one? No, I did not explain how to produce. It's a deep question, how to find all the kernel elements in for, say, so you consider some non-commutative algebra generated by this, by elements f1, f2, f3 with certain conditions, and what is the kernel? And the theorem is that the kernel is the ideal generated by that element.
But given the graphical representation of the vector that using the algebraic one, that one must be some view that
I don't know. I'm not sure that the question is. The question is if you have an action of a finite group, the question is how to split that object, how to split that theorem into the factors.
No, sorry, maybe my question was different. I mean, you are telling us that the graphical.
Where are you pointing? Here?
Oh, sorry, that there. Yes,
here.
Exactly. That graphical vector in the kernel.
Yes.
As an algebraic rewriting.
Yes. Is the
and
left
the
hand
rules
side?
for the rewriting, those are why this diagram is f1 squared f2 and this one is f1, f2, f1.
You know, those can be written as follows: f1, f2, f1. I'm sorry, f1, f2, f3 plus f3, f1, f2, f2, f1. So one of them is f1, f2, f3. The other is that one. This is no, it's not right. The left is f1, f3, f2 plus f3, f1, f2. That one is f1, f2, f3, f3, f2, f1. And the other is f2, f1, f3 plus f2, f3, f1. f1. So the symmetry is that I can symmetrize with, I can interchange 3 and 2. And I will call this by that, I will call this by, I'm sorry.
1 and 3 maybe. Yeah.
1 and 3, 1 and 3. I will call this by that name. I will call that by that name. I will call this by that name. So from f1 square, I produce f1 and f3 written in arbitrary order. So this is how you can recognize in this sum that expression. But I'm sorry, I have some plans. So I finished with one piece of that program. Missing it. Homology group. Yes, I explained the bilinear form on the top. So what is the bilinear form in the middle? You see, this construction is related to arrangements in real space, but the second form is related to arrangements in the complex space. It's a different definition, but it is defined for arrangements in the complex space, and it is the form S on omega I. So is defined for an arrangement of hyperplanes H1, Hn, n in the complex space. And in some sense, this is a semi-classical approximation of that form. So if you have a complex arrangement, you can define what I'm going to say right now, but it turns out that you cannot lift it to anything of that type unless your arrangement is a real arrangement. So in this case, this S is a bilinear form, on so right now I will write something, but I will do different things. So it is the complement. You consider the complement to the union of hyperplanes Hi, and then take it with complex coefficients. And here you take the sum of all homology groups to define that second combinatorial object. But let me define it.
So this S is what?
S is a bilinear form. S is a bilinear form on.
Also, you didn't.
I am going to define it now. It's, you know, I promised to define 3 forms, and I am yet on the first one. So it's defined differently. So I will. So let me define what is called FLN of arrangement. The flag space n flag space of the arrangement C in a complex space. So a flag and n flag is a sequence of edges. So it is F0, F1, Fn, and the last Fn is equal to Cn, where Fi is an I-dimensional edge. You consider this is the space of all linear combination of flags with some relations. F, L, N, C. The range of the arrangement is the linear combination space, on these flags, with relations. So what are relations? Relations are labeled by flags with gaps. Relations are labeled by flags with gaps, with one gap. So you take F0 to be F0, Fi minus 1, 0, then you don't have Fi, but you have already Fi plus 1, and then Fn. So assume that you have a flag with one gap. So it's an increasing sequence of subspaces, but you don't have one of them. Then a relation is in that space of linear combination is sum over all flags. Sum over all flags of the following form: F0, 0, F0, 1, F0, 0, I minus 1, then Fi you choose arbitrarily, then Fi plus 1, 0, and then Fn, 0. So for any flag with a gap, one gap, you have a relation in this space of flags. Namely, you say that the total sum of such flags where you fill up the gap in any possible way is 0. And this I is less than n. So the gap must be not at the end. So this is what is called the flag of space. So with every arrangement over in a vector space over any field, not necessarily real, you can define such a group. And then you define a bilinear form on it. Bilinear form on it is defined as follows. One more step. So assume that you have for any I1, IN, for any collection of n indices in the set of indices from 1 to n, and any permutation in Sn, you consider the flag f related to this I and Sn and this sigma. Namely, this is the flag where you take the first hyperplane sigma I sigma 1. Then you take the intersection of sigma I1 intersected with hi sigma 2, and you take the last term will be the intersection of I sigma 1 intersected with hi sigma n. So if you have a collection of n hyperplanes, then you can define the corresponding flag. And now if you have for any flag f, and any collection of indices I, you define the index of f and I to be 1 minus 1 to the power sigma if f I sigma is our f and 0 otherwise. So for any collection of n hyperplanes, you define the index of that collection of hyperplanes with an arbitrary flag. Namely, that index is plus or minus 1 if you can produce from those hyperplanes our flag. But otherwise, it is 0. And now you define the form on two flags, f and f prime. It will be sum over all indices like that. You write ai1, ain.
Seems to me that in the notation the sigma is missing because it's a bracket fi is something which depends on sigma.
Yes. No. You see, if I have I1, In, I have n factorial flags constructed out of n hyperplanes. Namely, I need to choose first, second hyperplane. So if I can choose such an ordering on this set that set of hyperplanes will produce this given flag, then I say 1 or minus 1. If I
it is f for some sigma.
Yes. If for some sigma you can construct this flag. So it will be a1 an sum over, and here you write the index of f and I and the index of f and f prime and I. So you have two flags, and then you define the scalar product. The scalar product is of the following way. So if you can choose n hyperplanes so that you can produce the first flag and the second flag from that collection of hyperplanes, then you take this monomial. And so you need to choose all. Yeah, I forgot to demonstrate this factorial, n factorial. So this is the definition. So for example, in this case, what will be a flag? A flag will be a point and the line. And what will be the second flag? The second flag will be a point and this line. And then, so I don't know, this A1, A2, A3. So in this case, from these two hyperplanes, I can produce the first flag and the second. So I can take this hyperplane and intersect it with the second, and it will be the first flag. And construct that flag and that point from the same collection of hyperplanes. And so in this case, this f prime s will be minus A1, A3. A1, A3. So this is another combinatorial construction of a form defined on flags. The full flags, you can identify with the n homology group of this complement using some technique. But so this is a purely combinatorial definition. And the formula is that the determinant of this S is equal to the product over all edges. And here, I'm sorry, let me change here. Now let me call this weights S1, Sn, B1, Bn. So the weights will be weights B1, B2, and so on. So now let us define the classical weight of L, which will be the sum of all Bi such that Hi contains L. So the theorem will be the product over all edges. It will be semi-classical weight to the power this discrete volume. Yes. So instead of this 1 minus a squared to the power L, you will have this sum of weights. And so again, this global characteristic, when you take determinant, will be the product of local characteristics. And in principle, if you consider in the first situation ai to be e to the power bi multiplied by some small parameter, which divided by 2, then it will be 1 plus h bi divided by 2. Then that determinant will become that determinant. So I everywhere subtract ai. Everywhere subtract 1 minus product of ai. So when I subtract 1, I will have linear expressions in B. So in some sense, this form is a semi-classical limit. Determinant of that form is the semi-classical limit of that form under this asymptotic limit. But there is no way to define, at least no known to me way to define on a complex arrangement anything which would count somehow crossing of walls and so on and so on. So this is my second. Second bilinear form, and I have 5 minutes to define my main object. So let me say very briefly. So what will be the determinant of the period matrix? So I will not tell you how to choose properly the domains. You see, I'm going to integrate multi-valued functions. So to have some answer, I need to choose univalued branches of those linear powers of linear functions on each domain. So the definition of the period matrix needs some considerations, but let me formulate the answer. So let us consider the determinant of the integrals of these differential forms omega I over domains. So you can choose properly the domains in differential form, so it will be a square matrix. And then the product will be the following. So you take the product, so it will be more complicated. So you consider the gamma function. So the product will be over all edges lying in Rn. There will be something else later. So it's gamma function. Now you take so in that definition I had A's, the parameters. So it will be the weight of an edge plus 1 to the power of this discrete volume. Now here it will be the product of all edges lying in the projective space minus Rn. You see, in principle, if you have an arrangement of hyperplanes, you can consider that in your arrangement the infinity also comes as a hyperplane. And so if you add to your hyperplanes this infinity, then you will have a projective arrangement of hyperplane in a projective space. And it also will have some edges, some intersection of your hyperplanes with infinity. And there you need to take, first of all, you need to take the weight.
You've got Rn take away
Rpn minus Rn, I'm sorry. And also I need to take, define this definition. So it will be sum of ai from 1 to n. I need to define the weight at infinity to be the minus sum of all weights in the final part. And so here I need to take all infinite edges and write it here. Gamma L A of L plus 1. And now,
There's no power.
yes, the same power, defined in the same way. Now, you see, these are integrals. They must depend on the size of domains. And so here I will write the product of critical values of, so let me write it here. The product of critical values on all domains, all bounded domains delta of all functions fi a. So what is the critical value of a function fi to the power ai on a bounded domain? So a bounded domain is a polygon. And you have this fi equals 0. You have a vertex, the most remote from this hyperplane in that domain, v. And then you calculate fi at v. And this will be called the critical value of the on that domain delta of the function ai to the power a. So if I have a polygon, if I have a power of linear function, then I can define the critical value of that function on that domain to be equal to the value of that function at the most remote point from that hyperplane. And so here I need to write the product of all critical values. So each integral is highly transcendental function, but the determinant is product of local things. And this is just value of a power of linear function at some vertex. This is not an integral. This is a value of a real function, of a linear function raised to some power. So my final words. Consider an example. So two domains, z1 and z2. The two functions, f1 will be t minus z1. F2 will be t minus z2. T minus z2. Now the function will be t to the power a1 t minus z1 to the power a1 t minus z2 to the power a2. Now the differential form, so in this case the period matrix will be 1 by 1 matrix, integral over the bounded domain of this t minus z1 to the power a1, t minus z2 to the power a2, and I integrate this with respect to the differential form t minus z1 divided by t minus z2, t minus z2, and a2. You know, I did not tell you how to choose properly the differential form, but in this case, this will be the differential form. And my formula says that this will be gamma of a1 plus 1 multiplied by gamma of a2 plus 1 divided by gamma of a1 plus a2 plus 1 multiplied by z1 minus z2 to the power a1 multiplied by z1 minus z2 to the power a2.
Is it true that that product is over bounded domain and the indices I from 1 to n?
Yes, the product is over all bounded domain and in arbitrary indices from 1 to n. N capital. So these are critical values. These are critical values. These are contributions from the finite edges, 0 and 1. This is the contribution from the edge at infinity. And so, in general, the determinant is of this local form. So this algebraic product of values of linear functions at some places. So despite you have maybe very complicated arrangement with very complicated individual integrals, the determinant of those transcendental things will be the product of local contributions. And again, the main problem is, what if a symmetry group acts on this arrangement? Then this period matrix will split into blocks. How to write the determinants of the blocks? One simplest example, one simplest example is this arrangement, product of ti to the power a minus 1, 1 minus ti to the power b minus 1, product ti minus tj to the power 2c. Then in that case, the symmetry group, permutation group acts on the indices from 1 to n. And then there is only one dimensional symmetric subspace in the space of the linear combination of the bounded domain. So, and in that case, the period of 1 by 1 matrix will be the following integral: 1 t1 tn 0, and then you put it here, and then it will be what is called the famous Selberg integral. Selberg integral. And this is the product of some gamma, some very exotic values of gamma of linear combination of A, B, and C, of great importance formula, this Selberg integral for many, many applications. But this is the determinant formula for the one-dimensional invariant block of that arrangement with respect to the symmetry group. And there is a general conjecture, very effective conjecture, saying that if you have an arrangement and if you have a one-dimensional invariant subspace with respect to some group action, then in that case the corresponding integral can be written as a product of local factors. For example, there are some elliptic versions of this conjecture, or some discrete versions of this conjecture where some Jackson integrals, some appear Macdonald polynomials, and so on. So this is what I wanted to say. I'm very sorry for being late. Thank you.
To make the dictionary a little bit with what we saw earlier. So what you call a hyperplane corresponds, in the case of the xi minus xj, to an edge in a graph, for instance. and the what you call an edge would be a partition. And these flags, would that be an ordered tree? If you take a complete flag?
I would say they would be orderings. Orderings. They rather would be orderings.
No, because the so you would have one hyperplane per edge of your graph, right?
Yeah, but every time
I know, maybe trees. Yes, you're right.
So you're
So, for
you're
example,
doing kind of the same-
H12 intersected with H, I don't know, 2, 3, 4, and then intersected with H13. So it will be.
So each time you throw Hij in the
It
in
is
the
a
chain,
construction
that
of
equals
tree.
Xi equal to Xj.
It is a construction of a tree.
Like,
Yes.
the word in other literature on arrangements, what you call an edge is usually called a face. And the arrangement of hyperplanes of the form xi minus xj equals 0. Each hyperplane corresponds to an edge in the complete graph on n vertices.
It's also called a flat in matroid language, and some of the theorems here can be extended.
I saw was Determinant, for instance, you have this BL where you have a sum over the that would be like summing over the edges which are contained in a component of your partition.
So there might be some combinatorial identities
Wonder if that
related.
would be interesting, at least in the for that particular arrangement, of course. I mean, this is more general.
You introduced the first bilinear form, you had this matrix, and then you said it's easy to see that it's positive definite, whereas what you showed, for the moment was that its determinant is positive. Is there an easy way to see that all its principal minors are positive as well?
No, it's. I said that the determinant is, yes, the determinant remains positive for all q modulo less than 1. But when q is 0, then it is the diagonal identity matrix. And so it was positive definite for q equals 0. And then when I change q, it always non-degenerate. And it was positive definite at the beginning. So I assume it will be positive definite always. Is it true? I think yes. If I have a positive if I have a matrix depending on parameter and it's of symmetric bilinear form and it's positive definite at some point and determinant is never 0, then it probably is positive definite. Modular mistakes.
And another question, so this flag construction, does it correspond to the usual Schubert calculus for the matrix A?
My first guess would be no, but maybe I should think more. I should think maybe, but my first answer is no.
Okay. So, thank you very much
you.
again.
Thank you.